Hi, I'm Robin and I'll be producing videos for this course, MIE100. I did my undergrad at the University of Waterloo in mechanical engineering, and I'm currently a graduate student here at this university. Throughout the term, I'll be producing videos like this one that cover concepts and problems which I hope you find useful. In today's video, I'll present 3 problems that were also shown during the live tutorials. Between the lectures, live tutorials, and these videos, I hope that you can find a system for problem solving that makes sense to you. The first problem is about the motion of a particle with a known velocity function. It states, the velocity of a particle traveling in a straight line is given as v equals bt plus ct squared. If s equals 0 when t equals 0, determine the particle's deceleration and position when t equals t1. How far has the particle traveled during the time t1, and what is its average speed? To solve this problem, we need to find the expressions for both the position and acceleration as functions of time. Here's what the velocity function looks like. I've plotted it out to make this problem easier to understand. However, you don't need to plot it out in order to solve the problem. We can find the acceleration of a particle by taking the derivative of velocity. That gives us the expression a at t is equal to 6 minus 6t. Plugging in t1 gives us negative 12 meters per second squared, which is the solution to the first part of the problem. The second part of the problem asks us to find the distance traveled during that time and the average speed. We'll need to find the position function in order to do so. We can find the position of a particle by integrating its velocity with respect to time. Taking the integral gives us s at t equals 3t squared minus t cubed plus a constant of integration which I call s naught. Because of the integration constant, the position function can shift up or down by any amount, and the exact amount depends on the initial conditions. Well, it looks like the problem gives us an initial condition. We're told that at time 0, the position is at 0. Substituting in 0 for both s and t shows that s naught is equal to 0. Now that we have the complete position function, we can solve the rest of the problem. This is where it's really important to read the question carefully. The problem is asking for the total distance covered, not the displacement. S at t is a function that tells you the displacement of the particle over time. To find the total distance covered, we can't just plug in t1 into s at t, and that's because the particle changes direction partway through. As a result, we have to solve for the distance in 2 parts. The first part is where the particle is moving in the positive direction, and the second part is where the particle is moving in the negative direction. To find the point where the particle changes direction, we're looking for this point where the velocity changes sign. You can see on the graph that when the velocity changes sign, the position function stops increasing and starts to decrease instead. Let's call that time t2, and we can solve for it without graphing by setting v at t equal to 0. From there, we find that the particle changes direction at the 2-second mark. Then, we can use s at t in 2 parts to find the total distance covered. The distance covered from 0 to 2 seconds when the particle is moving away, and the distance covered from 2 to 3 seconds where the particle is returning. The distance traveled in the first section is given by this expression, which is the final position minus the initial position. Remember, we're dealing with distances and not displacements, so we have to take the absolute value. Similarly, the distance traveled in the second section is given by this expression. Sub in the values and we get a total distance of 8 meters. Lastly, the average speed is found by dividing the total distance by the change in time. That gives us an average speed of approximately 2.67 meters per second. The next 2 questions are both about projectile motion. Whenever you're tackling a projectile motion question, you should always think about breaking the velocity into 2 components, the horizontal component and the vertical component. Each component has different equations that you can use, and I've written out some useful ones here. On the x-axis, the projectile will move with a constant horizontal speed, which gives you this equation. On the y-axis, the projectile accelerates due to gravity, so we have to modify the expression somewhat. And here's an expression for the vertical velocity with respect to time, and here's a function that relates the initial and final vertical velocity to the change in height of the object. Now remember, sign matters. These equations assume that the gravity vector g is negative and that no other forces affect the object while it's in flight. Now let's take a look at the second problem. It states, the buckets on the conveyor belt travel with a speed v. Each bucket contains a block which falls out of the bucket when theta equals theta 1. Determine the distance d to where the block strikes the conveyor, and neglect the size of the block. Remember that we always want to think in terms of horizontal and vertical axes. Let's use the center of the gear as a reference point for our coordinate system. X will be positive rightwards, and Y will be positive upwards. This problem gives us the initial velocity in both magnitude and direction. It starts out moving at 5 meters per second at an angle of 30 degrees below the horizontal, and after falling for a while, it hits the lower conveyor. We can break that velocity into horizontal and vertical components. The horizontal component is Vx equals v times cos 30, and the vertical component is Vy equals negative v sine 30. The initial position of the block can also be found from the geometry. The problem is asking for the distance d, which we would find by using the equation for horizontal position shown here. However, we don't know how much time it takes the block to fall, so we need to solve for that time first. To do that, we can use the equation that relates the vertical position to time, since we know how far the block has to fall. If we substitute in the initial height, final height, and the initial velocity, we get an expression that is only in terms of t. It's a degree 2 polynomial, so we can solve it using the quadratic formula, and that gives us the result t equals 0.294 seconds. This is how much time it takes the block to fall and hit the lower conveyor. Now we can find the distance d using the equation for horizontal position. We substitute in the initial horizontal position, the initial horizontal speed, and the time taken to fall. This gives us the answer of d equals 1.424 meters. Now for the last problem. It states, measurements of a shot recorded on a videotape during a basketball game are shown. The ball passed through the hoop even though it barely cleared the hands of player B, who attempted to block it. Neglecting the size of the ball, determine the magnitude VA of its initial velocity and the height h of the ball when it passes over player B. As usual with projectile motion problems, we can start by defining a coordinate system. I'll place it at the feet of player A. We don't know the magnitude of the initial velocity, but we can still break it into components. The horizontal component is VA cos theta, and the vertical component is VA sine theta. To solve for VA, we can use the fact that the ball has to pass through the hoop. In other words, the ball needs to have an exact position in both x and y at the same moment in time, which is time c. This will let us solve for the initial velocity VA. Since we want to force the ball to be at a certain position at a certain time, we'll use the equations that relate the position of a projectile to time. We can substitute in the initial velocities, the position of the basketball hoop, and the time t equals tc, since that's the time when the basketball reaches the hoop. This gives us two equations with two unknowns, so we just go on to solve for both tc and va. We find that tc equals 0.936 seconds and va equals 11.102 meters per second. Now that we know the initial velocity, we can move on to solving for h. If we try to use the equation for the vertical position, we run into a roadblock in that we don't know how long it takes to reach point B. To remedy this, we can use the horizontal position equation. Substituting in the horizontal distance to point B, as well as the horizontal velocity, lets us solve for TB, which is 0.78 seconds. Substituting that value back into the equation for vertical position gives us h equals 3.447 meters. That concludes this video. I hope that I offered a clear explanation of the tutorial problems. If you have any questions or comments, please feel free to contact me at my email address, rliu@mie.utoronto.ca. I'll see you in the next video.